Sorry, can you hear me? Can you also see my slides? Does it work?
Yes.
Okay, so then good morning, everybody. First of all, I would like to thank the organizers for inviting me to this conference, and I regret very much that I'm not able to be in Turkey, not able to be in Bodrum. And thank you to the organizers that they allow me, or they gave me the possibility to change the presentation to this online version due to health reasons. So sorry for not being with you. So what I'm going to talk about is iron-based superconductors, and I'm going to talk about two different systems. Two different systems. These are, let's say, the 1111 type systems and the 111 type systems. They are very, very different compounds, and also the aspect which I would like to discuss with you in the next minutes turns out to be very, very different in these two systems. So this is the outline of this talk. I will show you phase diagram now on single crystals, which we obtained for first series of these 1111 type crystals, and discuss in particular the nematic fluctuations, and arguing that there is a very strong coupling between these nematic fluctuations and superconductivity, which points to the real role of orbitals in these systems. I will show you some recent experiments where we measured strain-dependent thermoelectric transport, so where we have a direct access to changes of Fermi surface and scattering upon tiny changes of the lattice structure, so an intimate coupling between lattice and electronic degrees of freedom. And then if time allows, I will continue and will show you also recent results on lithium ion arsenide, which is a very peculiar, very nice system on the one hand, because it allows very detailed studies of surface science, so photoemission and STM studies. But on the other hand, it's really very much different from the other iron-based superconductors, also with respect to the phase diagram and the properties, and this I will discuss. And I will in particular discuss here evidence for nematicity, which is very much different from that what we found in other systems. So before starting, I would just like to mention the people involved in this work, a big team in our institute, starting from the synthesis of crystals. And Ria Kappenberger, she was really crucial, PhD student, crucial to find the first way to synthesize these large single crystals on these 1111 type systems. We do NMR, NQR. A large part of the talk will deal with nematic susceptibility to transport measurements, and here Federico Caglieres and Xiaocheng Hong were main players in the game. And then at the end, I will come to ARPAS, and most of you probably know Sergei Borisenko is the head of our ARPAS team. Okay. Iron-based superconductors, are they good metals or are they bad metals? And I think this question is not easy to answer. And it's very much different from the cuprates, where we think that all the systems behave rather similar. In the iron-based superconductors, there are big differences. If you just look at the resistivity, for example, you find systems which are really very nice nice metals, like lithium ion arsenide. So this is a measurement of resistivity. You have a large RRR, you have a tiny residual resistance. You can fit this resistivity behavior as T-square behavior. So this really looks a lot like a conventional, nice metallic state, and then you have superconducting state. There is, however, a clear exception from this rule. And this exception from this rule are these 1111 types of systems, in particular this lanthanum oxygen iron arsenide compound. And already in the first work, when this superconductivity was discovered more than 10 years ago, nearly 15 years ago, you see there is this upturns, and then you need to dope in order to get some metallic conductivity. And this remains the case till today. So I think this is the smallest resistivity I ever found in a single crystal on these 1111 types of systems. So you still see this upturn here. Then there is a strong decrease. You have these structural and magnetic phase transitions, which I will discuss in more detail later on. And then there's a decrease. And this already tells you that this increase and this overall huge resistivity is not extrinsic. So you change, you even open a gap, and nevertheless the resistivity decreases. So you have an intrinsic reason for an extremely bad mobility of electrons. You're we have a really bad metal in these systems. And what you have to do is to have to dope, and then at the end of the day, you end up with something which looks like a T-square and a nice metal. So in some sense, if you and this again, very old data. If you look on this doping dependence, this really looks a little bit like a cuprate. So you start from a very bad metal, and then you end up with metal upon doping only. So it's already telling you that you are far away from a conventional metallic state. And there's another experiment telling you something like that. So for example, if you start from the optimally doped compound here and plug in a tiny amount of impurities, superconductivity crashes down. And this again goes along with a localization of charge. Again, you immediately come again to a localized state when you plug in some defects in these systems. So that's really completely different situations than we have it in this lithium iron arsenide, far away from a good metallic state, very close to a localized state. I admit that I do not know a reason for that. So if you ask the theoreticians, they will tell you, okay, electronic structures are very similar. There's no reason for that. So the crystal structure of these layers is very similar. If you have a look on this, if you have a look on the structure, of course, there is a difference. So we have these iron arsenide layers here embedded between lanthanum oxide layers. This makes the system probably much more two-dimensional. It's also really from chemistry, it's completely different. It's not an intermetallic compound. It also makes it much more difficult to synthesize the crystals. Still, it is a system showing the highest TC. So these really bad metals, these systems where you really have to dope a lot before you get some reasonable conductivity, these systems show TCs up to 60 Kelvin. Much higher than that what you find in all the others, in lithium iron arsenide or in 122 and all the other systems which we are used to study. So it's an interesting system because it is a real high TC compound here, but this high TC emerges out of these very bad metallic states. If we are close to a localized state where the d electrons are not mobile anymore, of course, it's worth having a closer look on the electronic configuration in these local energy scales. And then you see this iron atom embedded within this arsenic tetrahedra. And this means you have also orbital degrees of freedom which play a role. So you have a crystal field splitting. If you then plug in these 6 electrons, you end up with these degenerate XZ and YZ orbitals. Okay, and this of course plays a crucial role. So you have this degeneracy of the orbitals. Okay, in a metallic system, it's our bands which are degenerated, but this of course is the source of a strong coupling to the lattice. And this is also well known. We have this phase transition going ahead, which you already saw in the resistivity before. We have a structural phase transition from tetragonal to orthorhombic, which lifts this degeneracy. And it's already argued a lot that these orbital degrees of freedom play a crucial role when discussing this so-called nematic instability in these iron-based superconductors. And in these 1111 type systems, in contrast to other systems, these structure phase transition, or this nematic phase transition, if you would like to call it like that, or this orbital order, if you want to call it like that, is well separated from the magnetic one, which occurs 15 Kelvin lower temperatures. That's already seen in the very early work which we did on powder crystals. Okay, so that's the starting situation. So we have these orbital degrees of freedom, we have these nearly localized states, very bad metallic states, and of course we have magnetism in the game in these systems. And the phase diagram which we also know for these. So for, again, fluorine doped 1111 type systems looks like that. So there's a revised version. We have synthesized a new series of polycrystalline materials recently, studied that mainly with NMR and with many other techniques. So you have the magnetic transition, which is rapidly decreasing here. You have this nematic transition, which is also decreasing. They are well separated. Separation becomes larger. Signatures of this nematic transition disappear in thermodynamics, disappear also in local probes. And then you have a superconducting dome here, which emerges out of the system. It's quite interesting to see that we really have an underdoped region here where we have no magnetic order and TC increases upon doping, and then we have the optimally doping here. So that's, again, it's a different phase diagram than that what we are used to for the other iron-based superconductors. I should also mention that we rechecked old data. So we took an NQR probe. So we go to the literature, look for all publications where NQR were measured, where measurements were shown. We rescaled all these data on these NQR lines. I can explain in more detail if you want, but message is that these phase diagrams also on old samples now fall on a single line. So we are quite convinced that this phase diagram is really correct. So it's polycrystalline material, because the main problem with these 1111 types crystals, because we are not dealing with intermetallics, the main problem is to get nice single crystals where you can do reliable and sophisticated experimental studies. And at least for these parent compounds, we had a breakthrough, and that is a couple of years ago. That is Ria Kappenberger doing a PhD. She found a way to synthesize these really very nice and large single crystals. And that's a very unusual way. It's based on abnormal crystal growth. It's connected to polycrystalline material synthesis. And then you have to do very special thermal treatments, very special alignment of materials. And everything is described in detail in this Journal of Crystal Growth article. And then you finally end up with these very nice, faceted, nice, large single crystals of this lanthanum oxygen iron arsenide. And that's the starting point of this additional initiative of us to revisit this system. Still, the challenge is that doping with fluorine is extremely difficult, and we are still working on that. There are some first progresses, so replacing oxygen by fluorine in this process, but the control for that we still do not have. What is more easy to do is to replace iron by cobalt. So then we can use the same process. We can produce single crystals now. The cobalt concentration which we found in the crystals corresponds very well to the nominal cobalt concentration, which we use to synthesize the crystals. So that's shown on this line. So we have now a series of samples as a function of doping. We, of course, know that this is, let's say, not the best superconductivity or best superconductors to which we expect, because on the one hand, cobalt doping is electron doping. We know that, of course, because cobalt has one d electron more than iron. On the other hand, it's an impurity, and I've shown you already how sensitive these unusual bad metals react on impurities. So therefore, we expect that superconductivity will be very bad in these systems. And that's also what we find at the end. So of course, what we can do now is we can use more sophisticated experimental techniques to study the phase diagram. And some results are published in this paper, for example, measurements of the thermal expansion, where we use a dilatometry to study both these structural phase transition, so that means the cinematic phase transition, and the magnetic transition. You can even see in the lattice. So you're just measuring the size of the crystal. You can also measure the magnetic phase transition. And you can follow that as a function of doping, and you can derive a phase diagram which looks like this. And as expected, superconductivity is lousy in these systems, strongly suppressed when you compare it to the fluorine doping. But this is just the effect of the impurities, which we expect. On the other hand, the phase diagram looks very similar. We have a magnetic phase transition. We have these structure or pneumatic phase transition, and then we have a superconducting dome. Okay, that's the phase diagram which we find, and we find it from various techniques, also from NMR and published now in these recent papers. That's not the end of the story, I should emphasize. So we are still working on that. We are still working on improving the single crystals. So we have now a series of the next step is a series of samarium 1111 type compounds, where we again started the cobalt doping. There's an entire series of samples that exist. We have now better superconducting properties here, because samarium also in the fluorine dope compounds leads to higher TC. And this is work in progress. And I will tell more on that in the next years, so hopefully. And in addition, we also have first steps towards fluorine dope crystals. Okay, that's work in progress. Now let's have a look on this aspect which I would like to emphasize today, and that's this pneumatic substitute. So having these single crystals now, we can follow this approach, which has been pioneered by Ian Fisher a decade ago on these 1-2 compounds, where he used piezo elements to apply a tiny strain of the sample and measure simultaneously the resistivity. And you can do that in different configurations as shown here. So you can probe different modes, and there you can really address in particular this pneumatic instability, or this pneumatic susceptibility as people call it. So if you then measure the resistivity as a function of these tiny strains, so look at the numbers, it's 10 to the minus 4 strain only, then you see the strong increase of the, or strong change of the resistivity as a function of this strain. If you plot the slope of these lines here as a function of temperature, you derive this divergence of the pneumatic susceptibility defined as change of resistivity divided by strain. Okay, fine. No surprise. So we are approaching this pneumatic instability. You can fit this with this typical Curie-Weiss law, and that's shown here that this is not so bad. So 1 over this pneumatic susceptibility follows a straight line, and this shows you just how good this fit is. So parent compound, no surprise, divergence at the phase transition. So such experiments you can now do on the entire series of crystals, and that's shown here. So you start from the underdoped compounds where you still see this phase transitions here. You go to optimal doped compounds and overdoped compounds. In all of these systems, in the entire phase diagram now, we see that the resistivity strongly depends on this on tiny strain. So the pneumatic susceptibility and pneumatic instability is relevant in the entire phase diagram of these systems. What you can do as next is you can have a look on these characteristic temperatures which you derive from these Curie-Weiss fits. Now you see here this divergence is close to this phase transition, to the structural phase transition. But what you also see is when you just follow these straight lines here, that these characteristic temperature, which you get from these fits, changes, becomes smaller, even changes sign, and then it becomes negative. So if you plot these Curie-Weiss temperatures from this fit, you clearly see this straight line upon doping, and you see that I do not see anything. You see that it crosses 0 close to optimal doping. And these are just these 2 examples: optimally doped compound where you're close to 0, overdoped compounds where it's negative. But so, and then of course it's straightforward to compare this to the superconductivity, to this behavior of the structural phase transition. In some sense, we lose our signatures of the real phase transition. There is no long-range phase transition when we measure specific heat, thermal expansion, or NMR. But if we take this characteristic temperature from this pneumatic susceptibility, we can follow this line down to 6%, and we see crossing 0 just at the 6%. In some sense, if you take this Curie-Weiss fit as a signature of, let's say, this characteristic energy, we have something like a quantum critical point connected to this pneumatic susceptibility, which occurs close to the 6%. So this, of course, relies somehow on fitting of the data, but you can also have a simple look on the data itself. So just maybe go back. So just looking at the numbers. So these numbers, this pneumatic susceptibility means the derivative of the resistivity versus the strain, which is much, much larger here than it is for the overdoped compound. So it's not only these characteristic temperatures which you get here, but also the absolute value of this pneumatic susceptibility, which changes in a very systematic fashion as a function of doping. And this is just a color plot of this pneumatic susceptibility for all these crystals which we have here. And it's apparent that you have 2 critical regions here. One is located close to about 4%, and one is located close to about 6%. So there are 2 concentrations where this pneumatic susceptibility diverges. And both are connected to peculiar points in the phase diagram. One is connected to the transition, to the quantum critical point, if you want, or the transition where the composition where the magnetic order disappears. So in some sense here you see that these pneumatic degrees of freedom are coupled to magnetism. And that's of course clear if you go back to my initial pictures on these orbitals. We know that orbital order and magnetism strongly comes together. There's a lot of theory arguing that indeed spin fluctuations are the driving force for this pneumatic instability in the iron-based superconductors. Here you see this coupling. But you see also that this is well separated from a second instability, and the second instability, or the second enhancement of the pneumatic fluctuations comes along at a composition where we have superconductivity. So you could immediately, just looking at this color code, you would say, okay, just measuring the pneumatic susceptibility, you see the superconducting instability, superconducting dome here, just from a normal state property. And this strongly suggests that indeed these pneumatic fluctuations might be connected also to the superconductivity or superconducting pair mechanism. Yeah. Okay, you can compare this behavior with these two domes to the situation, for example, in this 1-2 compounds where we did the same experiments and others did this as well. And you see there's a completely different phase diagram here where magnetism disappears. You have this enhancement of the fluctuations here occurring at the same doping where this quantum critical point for magnetism occurs. And that's really different. So you can really separate that. And this, of course, points to this peculiar role for the pneumatic fluctuations. It's peculiar for superconductivity, but I would say it's also crucial to understand very unusual normal state properties which we have in these materials. And this brings me to the second part of my talk, and this is dealing with the strain-dependent thermoelectric properties. So you can measure not only resistivity under strain, you can also measure more complicated transport properties under strain. And this, what we developed here is a technique to measure thermoelectric coefficients as a function of strain. So again, starting point is this piezo stack. We take the single crystals, put it on top of that. Now we apply a thermal gradient. So we have a heater here. So we apply a temperature gradient here. Using a thermocouple, then we can measure the temperature gradient, which we obtain by the heater. That's one ingredient. And using these contacts, we can measure the thermal power or Seebeck effect. And if you apply an additionally magnetic field perpendicular to this stack and measure the transversal voltage, we can also measure the Nernst effect. And this we did also for these samples. Again, the strain, the maximal strain which we can apply here is very, very small. It's below 0.1%. Nevertheless, we can measure changes of the thermal power, and that's just shown here. That's a typical experiment. What we do here. So we switch on heater, get a temperature gradient. Then we switch on this piezo, apply a strain. From this temperature gradient, we get a voltage here. This is the Seebeck voltage. If we change the strain, which we get an additional change of the thermal power gradient, we switch off the piezo. It make it a little bit negative. You see this change of the thermal power again, then switch off the heater. And you can do that at different temperatures. And here you already see a nice thing. So thermal power itself changes sign when you change temperature. The effect of the strain does not. It has the same. And the same thing you can do with a more complicated measurement, the Nernst signal. Here you even have to measure at different field orientations, minus and plus 14 Tesla. And again, you see directly in the raw data, you see the substantial change of these Nernst or Seebeck signals when you apply this tiny strain. And then you plot again this change of the thermal power as a function of this strain, so 10 to the minus 4. And then you see these straight lines here. And from these straight lines, you can derive again something like pneumatic susceptibility, now based on more complicated transport properties which are not measuring scattering anymore. They measure in detail Fermi surface, for example. Our Nernst effect is even more complicated. The main message here is, and that's really a take-home message in some sense, that these systems are so sensitive on tiny changes of the lattice constant, if you want, tiny changes of strain, that really the whole electronic system reacts. That's really far away from a conventional metal. again. So we really have a system where we have very, very strong coupling between lattice degrees of freedom and electronic degrees of freedom. And that's not mediated by magnetism. That's what we saw in the last time. So we can play our games now. We can plot now these derivative strain thermal power versus strain as a function of temperature. It's not a big surprise that we again see something like a Curie-Weiss behavior again for the parent compound, but there are already surprises. So if you look here at the absolute value of the thermal power, as already shown you from the raw data, the absolute value of the thermal power changes sign. And that's due to the fact that we are dealing with a compensated system. So we have hole and electron-like charge carriers which are of the same number. That's at least in the parent compound. So the absolute value of thermal power changes sign, the derivative does not. And this already tells you, and that's maybe also some, let's say, some question to theory. This already suggests that these nematic fluctuations are band selective. Apparently, they do not act in the same way on the negative and positive parts, or the parts leading to negative and positive thermal power. That really looks a little bit that they all mainly act on the electronic bands. So we have this increase. You can, again, do the same story as a function of doping. In these 3.5% doped systems, we have then a negative thermal power. So we have added electrons. So we have electron bands. So the sign is the same, but the size is different. You see, again, just here looking here at the absolute value, it's becoming smaller. If you go for the resistivity, the absolute value becomes larger when you add doping. So you already see we really measure something different here. So the concentration dependence is different from that from the kinematic susceptibility derived from the resistivity. Okay. We also did such experiments meanwhile on other 1 to 2 compounds, barium 1 to 2. You also see this increase of this change of the thermal power as a function of temperature. And it's remarkable that this intermetallic compound, which is so much different from this crazy oxide or oxo iron oxides, lanthanum oxide, iron arsenide, still has similar size of these derivatives. That also might be a message that we can really measure something which is rather generic for these systems. We will see. So strain-dependent transport, can we go beyond Curie-Weiss analysis? And we did first and I will not go in details here on all these concentration dependence, but just mention that that in principle we can learn a little bit more, and it's straightforward to do that. So in principle, the Seebeck effect can be written in the form that it's a product of a so-called Peltier tensor times resistivity in this way. And then this Peltier tensor is the energy derivative of the conductivity. And this energy derivative means that you're really very, very sensitive to details of the Fermi surface, of the density of states of Fermi surface. What's well known is if you have a peak of the density of states of the Fermi surface, the Seebeck effect becomes very large. And a similar formula can be written up for the Nernst effect. And if you now have a strain, you can then argue that, of course, you have two components for this Seebeck effect. A component which is strain derivative related to this Peltier effect, to strain effect related to the Fermi surface, if you want, similar languages or simple languages, and a strain derivative which comes from this resistivity part. So this is what we measure by measuring the strain derivative of the resistivity. And the message is both are of similar size. Sign is sign depends on the Fermi surface part for this guy here, but both are of similar size. So you really have an additional quantity here besides the nematic susceptibility which we are used to from the resistivity. And this is also, of course, the reason why we have these different concentration dependencies. You can go a step further and can take these measurements of resistivity, measurements of Seebeck effect, and can calculate the strain derivative of the Nernst effect. According to this formula. So that's all measured quantities, and all these measured quantities give this Yarrow curve here, and then you can measure directly the strain derivative of the Nernst effect, and then you see a one-to-one correspondence. And that's a surprise. It never works if you do it with pure compound. Again, telling you that these strain derivatives is really a very important aspect. That's really the most important aspect for these electronic properties of these 1111 type. And let's say the take-home message for these first two parts, that we have now the single crystals available. We are still working on having better systems. The hope is that we at some point will get really nice single crystals also for the systems which have the highest CC in these iron-based superconductors, about 60 Kelvin. But what we know meanwhile already is that we can clearly separate the magnetic instability and the superconducting instability with respect to their coupling to the nematic fluctuations. Both are coupled to the nematic fluctuations. We have a strong coupling between the electronic degrees of freedom and these strain derivatives. And I personally believe that this is mediated by orbitals. So this is 1111 type compounds. I will take the remaining time, still have a couple of minutes, to switch gears to completely different compound, and this will make clear that these iron-based superconductors are very, very different in their respective. And this lithium iron arsenide is very different. In the parent compound is already a superconductor. There is no structural phase transition, so no evidence for long-range nematic order, no evidence for long-range orbital order. There is no magnetic transition found so far in these systems. And still it's a nice superconductor. It's a very nice system for surface science. You can measure the superconducting gap with extremely high precision using photoemission, and this has been done by us, but many other people as well. You can also do very nice STM measurements in these systems. Okay, and there is a surprise. If you do a very detailed analysis of the superconducting state or the superconducting gap as a function of the position in K-space and plot this, and this is for the big pocket here for one of these, let's say the part of the Fermi surface in this system, plotted as a function of this direction, you see this line, and this apparently has two-fold symmetry. It's not a tetraagonal symmetry. It's only a C2. This looks a little bit like a broken C4 symmetry, as we, of course, used it in the systems where we have the nematic phase transition. Okay, that was first reported in this paper. We did also analysis of the Fermi surface, and also if you measure the size of the Fermi surface in the same experiment along X, X, and Y, you see a clear difference, which is of the order of about a couple of percent. A big surprise. We did more measurements meanwhile. We repeated the measurements with the same equipment. We also used a completely new type of detector, the so-called FESUMA, Fermi Surface Mapper, which is a very great method to do a simultaneously mapping of the Fermi surface with one shot. We used a laser source. We used also a synchrotron source here. Details are described in this very recent publication. And we also, using this equipment, we also can follow now the changes as a function of temperature in detail. This is just a Fermi surface. And now we're using a laser. We are close to the gamma point. We are measuring just the size here of this small pocket here of the Fermi surface, above TC, below TC, difference, and difference again clearly has a C2 symmetry. And again, we can now see this difference between which emerges now as a function of temperature. So that's just a situation where you clearly see this leading edge gap, and then we see this emergence of this difference, emergence of nematicity in the superconducting state as a function of temperature. Okay, and that's again a big surprise, and I have to admit we do not really understand what's going on here. No? So we can mimic this thing. We found this now in for all parts of the Fermi surface. We found it for the electron parts of the Fermi surface. We found it for the big hole pocket. We found it also for the small hole pocket. And I think from experiment, we did all what we can do to prove it, to reproduce it, to use different techniques to show that it's really there. There is also some kind of theoretical description, which was put forward by Andrei Shubikov in this paper here, where superconductivities, different superconducting components play a role to induce this nematicity. But of course, I think there's also question marks, for example, domains and something like that. Why don't we see any twinning here and so on? There's a lot of things which we really cannot answer. So what we wanted to do now, and what we did in the last month, was to look whether this nematic instability of the superconductivity, is it also showing up in these usual nematic susceptibilities? And here I will rush a little bit through the data. So what we also did is now measurements of the nematic susceptibility by doing this resistivity measurements as a function of strain. And the message here is, if you do that, there is nothing. There is no indication of nematic instability if you measure the resistivity as a function of strain. Here, these are some, then we add some impurities here, some vanadium, so some hole doping, some electron doping, and you still, everything remains small, no strain dependence of the resistivity. Just for comparison, the other very similar system, structurally very similar system, you really see this nematic instability here, and there's basically nothing in the lithium ion arsenide. So a puzzle. So we see the nematic whatever in the superconducting state from APES, but in the normal state, at least, we do not see anything. Then normal state. So let's just send the same data is described in this recent paper. The next thing which we tried was NMR. So we can also probe this nematic instability or the change of the orbital degrees of freedom, let's call it like that, charge distribution, by applying a strain and then measuring the electrical field gradient. That works very nicely in 1 to 2 compounds, where you can follow these, you can derive the nematic susceptibility also from, let's say, from this local probe. Also, you can do it in a superconducting state. So we tried to do the same, or did the same experiment, and again in lithium ion arsenides, try to see any indication of orbital degrees of freedom, of changing of electrical field gradients as a function of strain. And now we can really have a huge strain, which we apply here, and there's nothing. No evidence for increase of nematic susceptibility at low T. That's just the message. And even worse, then we did a further very tricky experiment. We used this dilatometry, looking for anomalies at the superconducting transition, which occurs here at 17 Kelvin. And this is basically noise, what you see here. It's very small signal here. And again, at the superconducting transition, there is no change of the lattice, no change of nematicity, visible at least if you measure the lattice constant. And just for comparison, if you do the same experiments, even in the strongly overdoped compounds here, far away from any phase transitions, you still see this very nice phase transition, and then you can replace it. You can show that it's just this nematic instability, which you show here. But this is not the case in this lithium ion. So there's no evidence for lattice distortion due to nematic order. And of course, then there was the idea that it's not a superconductor at all. So we measured it in the magnetic field. And indeed, in the magnetic field, we find huge anomalies and even some evidence for nematicity occurring. And this is the next puzzle which we are facing here for this lithium ion arsenide. Whether this is, measurements are in progress, whether this is connected to APES, we still have to settle. But that's, let's say, the first indication that we really have something also from macroscopic. But this already brings me to the end of the story. So just a summary. The first 2 parts I discussed this 1111 type systems. There, the main step which we have now is that we are able now to produce series of single crystals. For the first time, we can do sophisticated measurements. And the main message here for you is that we can clearly separate magnetic and nematic fluctuations, and we can clearly show that the electronic properties of these systems strongly couple to these strain dependencies, strongly coupled to the nematic instability, strongly coupled to the orbital degrees of freedom. And you can see that from the superconducting dome, and you can see that from all kinds of normal state properties which we measure. And there's clear that's not many of these instabilities, many of the bad metal behavior which we have there is not coming from magnetism, but it's instead coming from these other degrees of freedom. And then I flashed recent results on lithium ion arsenide, where we have this very surprising observation that we have a breaking of C4 symmetry if you measure photoemission in the superconducting state. So emergent, it looks like emergent nematicity in the superconducting state, again, pointing to coupling between superconductivity and nematicity, similar as we have discussed it in the other systems. However, all our usual probes do not show the same kind of coupling between electrons and strain, which we are used to for the other systems. And that remains a question mark how to combine these two observations here in the systems. And the magnetic field may indicate that there is something, but there we are currently working on it. So that brings me to my end. Again, thanks to all the people who contributed, and thanks to you for listening.
Okay, Bernd, thank you very much for your beautiful presentation. And questions, please.
Thank you, very nice presentation. Concerning your studies on the lithium iron arsenide and the Fermi surface deformation causing TC, you use basically a deep UV laser, I assume. What would be the pulse duration that you use?
So I think the first thing is for the first studies we use synchrotron mainly, no? And for the laser polarization, I know that Sergey did many experience on that for different polarizations. So I think that was not dependent on the polarization what we are shown there. So we see it for different things.
Yeah, no, I was saying the pulse duration, the pulse width.
The pulse duration. No, that was a
pulse,
CV laser. CV laser is first.
The pulse time duration.
Yeah, I think it was a continuous wave mode, as far as I know. Don't kill me. So please have a look on the paper. It's written there. Yeah.
Okay,
so
because if it's not a very short pulse, you have a mixture of mechanisms interacting, which are thermal and electronic. That's why.
Yeah.
Thank you.
Yeah. Okay. I agree. So, but you know, this is just an additional experiment. So we did the main experiments we did on the synchrotron, not using the laser. We just used this additional equipment which we have available here now to recheck the things. So it remains a miracle. So we have this two symmetry, and now we have it for many different configurations, and it seems to be very stable. I think that's the message which I can give you.
Okay, thank you. One last question, if any. Well, if not, let's thank Bernd again, and we have.
Thank you very much for listening.
For you as well.
And bye-bye.
And let's thank all the speakers of plenary session now. And Bernd, thank you very much. And well, the session is closed. The next one is at 10.